Hola a todos, buenas tardes. Muchas gracias por estar con nosotros esta edición de y organizamos para álgebra temáticas de la unidad. En este, nosotros un placer ponente, Mike, el tema We Can Clones and Their una reseña del profesor doctorado en la Universidad en Alemania. Se realizó donde lo realizó en teoría de clones bajo la dirección Poschel, dos estancias de investigación en la Universidad 2013 a 2000, con Karin Quast, 2014 a 2015, técnica de Viena, bajo la dirección Gernot del 2004, trabajó en la Universidad Johannes K. Linz con actualmente de Viena como departamento de metas y geometría, con más de 30 publicaciones y ha dado en nacionales. Pertenece al científico de conferencias BL y multiple valued logic international son conceptual lectures. Pertenece al comité directivo de las conferencias workshop desde 2020, presidente del comité multivalor MBL. Se desarrolla en torno de la informática general, en práctica y desarrolla universal, temas funcionales y clones, y sistemas relacionados, estudiar los problemas de decisión en el contexto de satisfacción de restricción CSP. Le interesan las conexiones general con la, por ejemplo, categórica de variedad de álgebras y con los problemas de reconstrucción clones en numerales. For pleasure. So thank you so much for hearing.
Okay. Something wrong. Because I something on the
Do you know what's the problem? The red. Are you on?
yes, I can say something.
It's good.
Yes. Yeah, see.
So
Yes, I will. Okay. Bienvenido a mi plática. It's a great pleasure to be here. I'd like to thank the organizers of this seminar to give me the chance to give a talk here. The talk will be in English. I hope this will not be a major inconvenience for you. It's going to be about a topic that's related to kind of so this is about weak bases of relational clones. Relational clones are an algebraic structure. Weak bases are something like generating systems in a very specific way, which I'm going to explain. And the end of the title is that we talk about uses of weak bases. I have the clicker here. So about applications of these things, and these come from theoretical computer science and more precisely from complexity theory. So I've structured my talk into 4 parts. There will be quite a lengthy introduction to tell you why I'm going to do the algebraic stuff that I'm going to go into. Then there will be the meat of the algebraic theory that I'm trying to tell you. And then I will go into some applications where weak bases have been used in the past. And I have a fourth section where I will have a look at future problems for investigation. So let's start with the motivation. It will be fairly general, and I try to keep the background very low. What are we looking at in computational complexity theory? We are looking at computational problems, Q, and we want to compare their difficulty. And when I mean difficulty, I mean relative difficulty. We have no absolute notion of something is difficult and something is easy. We can only say that something is at least as hard as something else, or this is at most as hard as this. So we usually write arrows for this, or we write a less than or equal sign, indicating that this relation will be a quasi-order, so it will be reflexive. Each problem is at least as hard as itself, and it will be transitive. So if something is at most as hard as something, and the next thing is at most as hard as the third problem, then of course the first problem will be at most as hard as the third one. And I will try to show how we do these comparisons by way of some examples. No funciona? Yes. Okay. Good. In case there's some real complexity theory people in the audience, I will apologize. This is not very precise and correct. I try to deliberately pick some examples which you may be familiar with in real complexity theory. For example, you cannot work with real numbers because there are some representation problems there on computers and so on and so forth. I'm not going to go into these details. Let's compare the 2 following problems. You're given a quadratic equation. What does that mean? You're given the coefficients of the quadratic equation. The question is, give me the real solutions of this equation. So that's a problem which you can ask to compute. And there's another problem. I give you an elementary function in some way. I don't tell you how. And I ask you to determine the real roots of that function. Which problem is the harder one? Well, obviously, this one is the harder one, because when I can solve this problem, I can also solve this problem, because mainly every instance of the problem almost immediately is an instance of this problem. I mean, an equation is not an instance of a function, but I can turn this equation into, I can turn the coefficients into a quadratic function, and the root of this quadratic function is exactly the solution of this problem. And of course, the quadratic function is an elementary function. So we have less than or equal in this direction, because almost immediately every instance of this problem is an instance of this problem. Now, this is not the only way how we can compare problems. We can be a bit more sophisticated. Here I have modified the second problem, that we are given a circle in the plane, and we have some straight line, and I ask you to determine the points of intersection. I'm not going to talk how the circle is going to be given, how the line is going to be given. I mean, there will be some parameterization of the line. There will be some equation that tells you what the distance of the circle points to the midpoint is. And how are you going to solve this problem? Well, you're going to take your parameterization, you solve it for one variable, you plug in the variable into the equation for the circle, and then you're trying to find the solutions for it, and these solutions will almost immediately, if they exist, give you the points of intersection. The point of all of that is that when you do this, the equation that you're going to get will be a quadratic equation. So you can easily transform this instance of the problem into an instance of this problem, which you can then solve, and then you have a solution for this thing. So easy transformations turn instances of this thing into instances of this thing. That's why this one is at most as hard as that one. Third example, I'm going to go back to the elementary functions. Problem 1 is find points of intersections of two functions. Problem 2 is determining real roots of one function. Which one is harder? Well, none of them, because there are easy transformations both ways. First of all, if I have two functions and then I can form the difference of them, that's still an elementary function, and the roots of this difference function are exactly the points of intersection of the two original functions. And the other way around, if I have one elementary function, well, then I use this f as my g, and the h, I take the constant 0 function, which is also, of course, elementary. And so I turn this instance in that instance, and I can solve this one to solve this one. So it can happen that with respect to these transformations that we are applying, two problems are equally hard. These easy transformations that we're going to use to compare the relative difficulty are called reductions. And the kind of reductions that we're going to use depends on the kind of problems that we're studying or which aspect of the problem we're interested in studying. So I've prepared here a list of several types of computational problems. For example, there are decision problems in computational complexity theory which ask, is there a solution to your problem? You have to decide yes or no. You don't have to find it, you just have to decide whether there is one. There are counting problems asking how many solutions do you have? Of course, if you can count, you can usually answer this question because you can say, okay, I count. If the number of solutions is larger than 0, then there is a solution, otherwise not, right? Then there are search problems, which ask you, actually find me one. Don't just tell me whether there is one or not, whether there is a root, give me one. Then there are enumeration problems, which ask you, give me all the solutions. And well, mostly we're interested in answering these problems efficiently, since there can be problems that have very many solutions, even if the input is finite. There can be exponentially many solutions in terms of the size of your input. You cannot expect that you can finish the enumeration of all the solutions efficiently, but efficiency in this case means that you list all the solutions with polynomial delay. That means the time that you have to wait between one solution and the next solution is efficient. And there are other variants that are studied. For example, there are approximation problems. Don't find an exact solution, find something that's close to a solution. There are optimization problems. Optimize certain objective functions on the possible solutions of the problem. So that requires, first of all, that you have to be able to decide whether there's a solution at all. And each of these problems come with their own kind of suitable reduction notions. And there are many more in theoretical computer science. Computer scientists are very, very prolific in finding new problems and defining new notions of reductions and defining all these things. So I've prepared here the corresponding or the most often used kinds of reductions that are used for decision problems. One usually uses so-called many-one reductions, which means I take my smaller problem P, I take the instance, I transform it with my easy transformation into an instance of the harder problem Q. And then I decide the instance of the harder problem Q. The answer is yes or no. And then I'm required that the yes or no answer is exactly the right answer to the original problem. So I'm not able, for example, to answer no if the transformed instance is yes and vice versa. I have to give the exact same answer. And then there are some technical notions. This whole transformation should run in polynomial time. So these are p-time many one reductions. You can also measure efficiency in terms of this computational space that you use. So there are log space many one reductions. Log space implies that it runs in polynomial time. So there are different variations what you can do. When you count, there are other reductions which are used, so-called Turing reductions, where you can compute. And these are usually, you can best think of them as kind of a computer program that you write. And you are allowed to use a black box algorithm that solves the harder problem and count the complexity of calling the subroutine with a constant amount of time or steps, computational steps. That means you can use several instances of the harder problem, solve them, take the answers. Counting means you get each time you get some number as an answer, and all these answers that you get, you can use again and compute with them, and all in all, the whole thing should run in polynomial time in the size of the input. That's the kind of reductions that you use for counting. This is much more permissive than what is done with decision problems. But there are also other reductions for counting problems which are stricter, so-called parsimonious reductions, which are closer to those here. Namely, you transform the instance of the easier problem into an instance of the harder problem, but you're required that the answer of the transformed instance is exactly the number that you're looking for. So you're transforming, you're counting, and you're requiring that the number that you get, the counted number of solutions, is exactly the answer to the original problem. These are so-called parsimonious reductions. Now, I don't want to go too much into detail. For search problems, you also use Turing reductions. For enumeration problems, you could again use many one reductions. For optimization problems, there are specific reductions, so-called approximation preserving reductions, approximation preserving Turing reductions, where you're allowed to compute with the results, polynomial time approximation schemes. Well, all in all, if you feel like this guy, that this is all like very technical and complicated, then there's good news and bad news. The bad news is, yes, it is, if you really want to use it. The good news is we don't need to care, or I don't want to care in this talk, because we want to abstract away from the technicalities. I want to show you that algebra is able to abstract away from these technicalities that computer scientists have invented. As a comparison, our problems are like points on a map, and the reductions between them are like the paths that connect the points on a map. But the maps can change according to the purpose that you're using them for. For example, this is a standard map of some part of Mexico City. So you see some big streets here, and maybe I think this is probably a train line or something. But if you change it, for example, to a bike map, you will see that there's some differences. Some big streets become much less pronounced in the picture, and some other ways appear that haven't been there before, or at least not as prominent as in this map. Or if you change it to a traffic map, all of this stuff here becomes very gray, and other paths become highlighted. So it changes according to the purpose that you're looking for. It depends whether you want to go very slowly by bike and enjoy nature, or and this enables you perhaps that you can pass through a narrow lane like this one. You could pass through it by walking or by a bike, but you cannot pass through this narrow lane with a fast car. But on the other hand, with a fast car, you maybe can directly use this route without having to take uh, the route via an intermediate problem p hat. With a fast car, you're allowed to use a motorway where you can drive fast, which you're not allowed to do when you go by bike. You're not allowed to go with a bike on a motorway. I mean, at least in Germany, you are not. I don't know about Mexico. And there are differences, like here, you are not able to pass through with your car, and here you are not allowed to go by bike. And the same happens for your computational problems. Sometimes you're not able to use some connection because maybe you're not able to prove it, or there's some obstruction for that. Or sometimes you're not allowed to because you're interested in a certain aspect of your problem, and then using a certain reduction is not permissive. It just doesn't work for the kind of analysis that you want to do. If you use a big bus to carry all your friends around, you probably cannot pass through this bridge, which you can only cross by walking, right? Now, our maps, on the maps, we will have as points the problems, but I will take a more specific look at them. In complexity theory, many problems have a parameter, at least one parameter. Sometimes there are more of them. And many computational problems take as a parameter a set of relations. Relations are sets of tuples. You might think of an order relation or an equivalence relation or a graph between points, but we may also allow ternary relations or any number of inputs of coordinates for our relations. For example, a very prominent type of problems in theoretical computer science are so-called constraint satisfaction problems. I think I should write this down because this abbreviation will appear often. Constraint satisfaction problem. And these in general look as follows. This is a logical way of looking at them. The instance, your input to your problem, is a formula. It's a conjunction, a finite conjunction of relational predicates. Like in first order logic, you're using some atomic relations. And in these atomic relations, you're allowed to plug in variables from a fixed set of variables, say x1 up to xn, in some order, however you want. And then you're required, or you're looking at the solutions of this problem. These are all evaluations of these variables in the places of the predicates, such that actually every atomic predicate becomes true. These are the solutions. So these things here are the constraints, and the evaluations of the variables with real values from the base set. This is the base set where the relations live. These are the solutions. And then for this kind of setup, there are different kinds of questions that you can ask. You can ask, is the solution set non-empty? Is there a solution? That's a decision problem. You can ask, how many solutions are there? That's a counting problem. You can ask, please enumerate me all solutions. That's an enumeration problem. You can ask, find me one. That's a search problem. You can try to minimize some objective function on the set of all solutions. That's an optimization problem. And there are many more variations on this. Sometimes there are additional things in the input. Sometimes people look at only specific solutions, not at all solutions, specific subsets, and then you can do the same thing again. You can have all these variations again. So our points on the map are these. Oh, I missed something. The atomic relations, how are the atomic relations related to the parameter set R? I'm only allowed to use specific relations here. I'm not allowed to use all relations, but only those which are in the parameter set. For example, if in the parameter set I only put in order relations, then it means I can only express order constraints. I can say one variable is less than another, and another variable is less than another, and another variable is less than another. Or I don't know, if the relation represents the edge relation of a graph, then it says one variable and one variable is connected by an edge in your graph. And then you can say there are several consecutive edges and such things. So we're going to fix the problem type P. We're going to fix the base set for the relations. And as a disclaimer for the whole talk, the base set will always be finite. So we are only looking at relations on finite sets. The different points on the map that we're going to connect are the different parameter sets describing different computational problems. And the connectors are the chosen or allowed reductions for the problem. Now the question is, if we're using, what is the kind of level of zooming in into this map that we're going to use? Because if we're going to use all relations on a finite set there are countably many different relations. If you take all subsets, that's already uncountably many points. Maybe this is too much for our map. And here we're looking into what's usually done in the literature. For example, for the decision version of constraint satisfaction problems, there's the following theorem proved by Jevons. When you have two kinds of parameter points, Q and R, so these are both finite sets of relations, and if you know that every relation in Q has a so-called primitive positive definition in using only relations from R, that means you can write the for all relations in Q, there's a possibility to write a definition of this form. x1 up to xm belongs to the relation if and only if. And now there appears a logical formula, and the logical formula is of the following form. You have a finite conjunction, sigma 1 of some variables, some of those, and maybe some others, and sigma 2 of some variables, and so on, finitely many of them. This is a so-called conjunctive definition, because I only use conjunction. But now we're allowing, there's an existential quantifier here. We're allowing to existentially quantify some of the variables that appear in these predicates. So we're allowing some existential prefix here. Say m, no, m is already taken, k. If you have such a definition, that's a definition that uses only existential quantifier and conjunction. And possibly I'm allowed to say finitely many of these variables are equal. So for example, I can say y equals x1 and I don't know, maybe I should use a concrete one. Okay, z3 equals x1 and x2 equals x5. I can use explicit identification of variables. This is the kind of expressibility that I'm looking at here. If you have such a kind of expressibility, then Jevons' result tells us there's a permissible reduction between the CSP decision problem parameterized by Q and a CSP decision problem parameterized by R. By the way, this is also true for counting problems. This is another result by Bulatov and Dalmau from 2007. if you have this same kind of expressibility, then the counting problem reduces with respect to Turing reductions to the counting problem parameterized by R. But I want to stress here, this really depends on the reduction that you're using. If you're using the more restrictive so-called parsimonious reductions, then this result is no longer true, or it's not known to be true. Nobody knows whether this is true. Probably it's not true, but it's just not known. So the kind of compatibility that you want to have depends on the kind of reduction that you want to use for your problems. And I show you a very modest assumption here, namely one that works for very many CSP type problems is just conjunctive expressibility. Conjunctive expressibility means that I don't have this existential prefix here. For example, if I have a definition of the relation tau in terms of the relation rho, in such a way, if I have a definition of the relation sigma in terms of the relation rho, and now you give me some instance of a constraint satisfaction problem which uses tau and sigma, then I can almost immediately rewrite this into a formula that only uses rho. How do I do that? Well, if I read tau x1, x2, then I store these variables x1, x2, and then I look at the definition and I plug in the variables in the appropriate places. And this shows that I can rewrite this formula as a formula that only uses rho. So that's now an instance of the problem parameterized by rho. And I can do this very fast because the space that I need to store, I only need to store this little bit in order to write this. And since this little bit in comparison to the whole formula, which will be usually very long, is very small, you can do this in logarithmic space usually. So this means, in this case, these two formula, which you can easily derive from each other, they have the same solution set. And if the type of problem that you're looking at depends only on the solution set and not on some other input, then you get a reduction with this kind of compatibility. We're going to be a little bit more permissive. We're allowing expressibility with conjunctions and these explicit identification of variables by explicit equality predicates. So the assumption that I will make is that the problem I'm looking at is of the form that it is compatible with this kind of expressibility, that somebody can prove for this particular problem whenever the relational parameterizing set Q and R express in this way, then the chosen reduction is such that the problem parameterized by Q is at most as hard as the problem parameterized by R. So this is the burden that I place on the user of the theory. That's the assumption that I'm going to make. In particular, if I have that these two sets are equally expressive in terms of conjunction and equality, so if I can not only express every Q relation through relations of R, but also vice versa, then that means that I get comparability reductions in both ways. So the two problems do not differ from a complexity perspective. They're kind of the same. And that gives us the answer to the question, which map resolution should I take? I don't consider all finite subsets of relations, but I only consider them up to the equivalence defined by this equality. When they generate the same other relations using conjunctive equality definitions, then we consider the relations the same. And this is the map resolutions that we're going to use. And sets of relations which are closed under definability by conjunctions and equality are so-called weak systems with equality. And that's where algebra starts. So we can now completely ignore computational problems. we will only focus on these kinds of expressibility relationships. So the algebraic theory will start I will start with an overview of Galois connections, which relate sets of relations that are closed under certain logical constructions with functional counterparts. And this is the theory, the algebraic theory, that we will use in order to express or in order to establish these expressibility results. The oldest result is from end of the 60s by Bonaccio, Kaluzhnikov, Romov. If you use existential quantifier conjunction and equality, like here, then if you consider relations that are closed under these kinds of definitions, then on the other side, you have objects which consist of total operations. Operations means functions. I'll go into that in a moment. That's something of the form of map from A to the n into A. So it may have several inputs. And on these sets of functions, you have some kind of algebraic structure, which we call clones. And you know, when you work with Galois connections, then on the two sides of your Galois connection, you have closure systems. And on this side, you have closure under this kind of definability. And on the other side, on the algebraic side, you have a closure system which is defined by the property of being a so-called clone. Now, if you want to get rid of the existential quantifier, which we want to do, existential quantifiers are difficult from a complexity point of view, then we need to change something on this side. We are weakening the closure property on this side, so we have to be more permissive on this side. And that means we're moving from total operations to partial operations. And then there will be algebraic structures appearing, which are so-called strong partial clones. And that's a result by Romov from the 80s. If you want to get rid of the equality predicate, then you can go further. There are also results like that. Then you move into the realm of hyperoperations. A hyperoperation is not really an operation anymore. That's a function which can have several values on one input argument. So it's like closer to a relation than a function, actually. And if you want to remove all of these two and just get to conjunctive definitions, then you get to so-called partial hyperoperations. So you have to combine these two things. Now I draw you some smiley and frowny faces here. Ideally, we would want to go here because this is the best from the computational point of view. But the problem is then we have to deal with partial hyperoperations. And I'm not really sure if anybody knows anything about these things, except for that we have this Galois correspondence, but I think there's not much theory about them. At least I don't know nothing about them except this result. Here again, we have the problem of hyperoperations, and we have the existential quantifier, so we don't want that. And here, okay, this is nice. A lot of things are known about so-called clones, so this is nice, but this is bad for us because it uses the existential quantifier. So this is the row that we need to focus on, the weak systems with equality and the so-called strong partial clones. So this is what I'm going to tell you about. So what are the objects that we're going to look at? On the left-hand side of the Galois connection, we're looking at partial operations. So a partial operation is a function with n arguments. The output is of the same kind as your arguments, but it is not necessarily defined on every tuple of n arguments. Formally, I would specify this as follows. I fix the arity, I fix the domain, I fix the set where I live, and I fix the function defined on the domain. But I will usually write something like this for a partial operation. The number of arguments is called the so-called arity of the function. So we will speak of n-array functions or operations. The set of all partial operations I will denote by PA. And then we want to get to these clones and strong partial clones. So we need some algebraic structure on these functions. And what can you do with functions? You can plug them into each other. Like in the same way, if you may be familiar if you have transformation semigroups or if you have permutation groups, what can you do with them? What's the algebraic structure? You can compose them, right? Now here we have partial operations and they have multiple inputs. So we have to take care about this. If we have an m-array partial operation, so it has m inputs, then we can compose it with m other partial operations fi, f1 up to fm, and each of them again has some domain on which it is defined. So how should the composition work? Well, first of all, I need to make sure that the input works for each of my functions f1 up to fn. So I will consider the intersection of the domains of all the partial operations that I'm using as the input here. And then that allows me to form this m tuple of results. But this m tuple of results is not necessarily good enough to be used by the function g. So I need to ensure that this result that I get is actually in the domain of the outer function g. And that's what I will require. I will only look at these tuples. This gives me a new domain of an n-array partial function. And this n-array partial function works then as expected. You take the arguments, put them into the functions f1 up to fn, m, and then feed the result into the g, and that gives you again an element of A. That's composition of partial operations. There's a second operation that we can do with partial operations. Namely, we can make the domain smaller. We can just say, okay, it's not defined on this big set, it's only defined on a subset. That's domain restriction. So the function completely stays the same, just the domain gets smaller. And there's a third important ingredient. We need to have some constants, so to say, which play a special role. These are the so-called projection operations. They are always total, and they just output a single particular variable. So if you go back to the analogy of transformation semigroups or transformation monoids, then the things all would be unary functions of one input, and then the constant. Which unary constant would you get? You would get the identity operation, because there would only be one variable and the function outputs exactly this one variable. So that's the neutral element with respect to composition of functions of one variable. And here, these kinds of things play the same role for multi-array functions. Then we have total operations. Total operations are just partial operations that are everywhere defined. Everything stays the same. The composition gets much easier because we don't have to worry about the domains anymore, because I can just take the functions, take their results, plug them into the G. It's everywhere defined. There's no problem with that. And again, we have projections. Of course, we don't have domain restrictions, because if I restrict the domain of a total function, then I would get a partial operation. That's not where I want to go. So with the help of these things, I can now define the algebraic objects that we're looking at. A partial clone is any set of partial operations that is closed under composition of partial operations and contains all the projections. So this is like the analog of a transformation monoid for multi-array partial operations. Then there are strong partial clones. Strong partial clones are additionally closed under the other operation that we can take, namely making the domain smaller. So that means there are more partial clones than strong partial clones, because this is an additional requirement. And then there are clones. Clones are always sets of total operations. So They are just those partial clones which only consist of total operations. So O of A is the set of all total operations on A. And here the requirements are again closure under composition and to have all projections. That means what can you do in a clone? Well, you can in a clone you can build term functions. You can build iterative expressions of the following form. Oops. X3, maybe X1, something, and maybe it's ternary. So let's use X1 again. You can form such expressions with given functions in any way you want. And any new function that you describe in this way, any term function, remains in your clone. That's what you can do in a clone. And in a partial clone, you can do the same with partial operations. So now we need to look at the algebraic structure on the other side of the Galois theory. We have relational clones and so-called weak systems. Relational clones, they are both sets of relations with certain closure properties. And the closure properties are, we require the empty relation to be there. We require the equality, the binary equality relation to be there, which we call diagonal relation. And we require some logical closure. So in the case of a relational clone, we require closure under primitive positively definable relations. So when we are allowed to use the existential prefix, and for the weak systems, it's exactly the same, but we're weakening this closure property. We are only allowing conjunctive definitions. And because we anyway require the equality predicate here, this subsumes that we have conjunctive equality definitions. And now I have to tell you what is the connection between the two things, between the functions and the relations, because in every Galois theory, you need two kinds of objects and you need a relation which connects them. Like in classical Galois theory, you have the automorphisms of a field, and these are on the one side, and then you have the elements of the field on the other side, and you need a relation which combines the two. In the classical Galois theory, the relation is that the automorphism fixes the point. Here we need a relation which connects some kind of function and some kind of relation, and that's the notion of preservation. And this works as follows. We have a partial operation of n arguments. We have a relation of m arguments. We say the function preserves the relation if the following universally holds. Whichever matrix you come up with of format m by n, such that all the columns of the matrix form tuples which are in the relation, and all the rows of the matrix form tuples which are in the domain of your function. Whenever you have this situation, you require that, well, the rows are in the domain of your function, so you can apply the f to the row. To each row, you get as many results as you need as inputs for your relation. So the resulting m tuple, you require that this thing ends up still in your relation. This is the closure property which connects functions and relations. This is not very well visible now here. I'm sorry. Maybe we can shift the... yes, if you move it to the very top, then that works. Thank you. Okay. So for every Galois connection, you have then Galois operators, which connect the one side to the other. So we can now take any set of relations and connect them, turn them into a set of partial operations. Namely, what are we computing? We're computing all the partial operations, preserving all the given relations. And we are calling these things so-called partial polymorphisms. Now, you can do this, of course, with total operations too. So you intersect the partial polymorphisms with the set of all total operations. So you're looking only at the total operations, preserving your relation. Operations. You throw away all the partial operations, only take the total. And the opposite operator, which changes functions into relations, is the so-called. You take a set of functions, possible, and you construct all the relations being preserved by these functions. We call them the invariant relations. So these are the between both. Oops. Can you perhaps click on the? Yes. Thank you. These are the two connectors for this theorem here. For this side, we use pol and inf, and for this line, we use inf and p-pol. I was too far. Maybe. Can we move it a little bit so that we see this completely? Yes, thank you. Okay, so now we have the theorem of Romoff from the 80s. If I take any set of relations, the partial polymorphisms form a strong partial clone. And this is the easy part. The hard part of the proof is every strong partial clone actually appears under this Galois connection as set of invariants of some, as partial polymorphisms of some set of relations. Namely, I can always take the invariants of this strong partial clone. And on the other side, the relational characterization of this Galois connection is every invariant set of any set of partial operations is a weak system with equality, so it's closed under conjunctive equality definitions. And every weak system appears in this way. That means whenever I have such a weak system, I can write it as the invariance of some strong partial clone, namely the strong partial clone given as the partial polymorphisms of the system. Okay, good. Now, well, I think if I only have 5 minutes left, then I'm going to jump across this slide. And I will tell you about this slide probably here.
that inf of column S are the invariants of F, and the invariants of F are the associated relational clone of the clone that I'm starting with. So on the other side, I'm looking at all weak systems with equality that generate, in this sense, a given relational clone. And the interesting property of this interval that this thing has a top element translates to the fact that this set of weak systems has the smallest element, so there's the smallest weak system with equality, which generates this relational clone. And every subset, every finite subset which generates this weakest element is the so-called weak base of the clone or of the relational clone. And it has the property that it expresses conjunctive equality-wise in every other element here in this interval. Yes. So that's the connection to the complexity theory. When we're starting with a finite parameter set of relations, we can look at the polymorphisms of the relations, that's a clone. We can look at the associated relational clone. We can also look at the partial polymorphisms, so the strong partial clone with its associated system with this one will then be generated by this parameterizing set R. Because we're starting with a finite set R here, there exists such a finite set W which parameterizes this bottom element among these strong partial clones. And now, what happens if we look at the total part of this strong partial clone, given by this parameter set R? Well, if we intersect the partial polymorphisms of R with the total operations, we cancel the partial and we get just the polymorphisms of R. Polymorphisms of R are exactly our F. So that means this P here is a strong partial clone whose total part is F. So it belongs to this interval, and therefore it is below the top element. And that's why, if I now apply the Galois theory and the Galois operator on both sides, then I know that this weakest weak system sits below the weak system generated by R. And that means, because W is a subset of its generated weak system, that tells us that this weakest system is expressible in the conjunctive equality closure of R. And these are exactly the kinds of expressibility relations that we need for our complexity applications. Because by our complexity assumption, we know that now this is a weakest hard problem among a whole class of different problems. Because when we can prove that this problem is hard, each other problem with this assumption also is hard. And this is actually the magic behind this whole method. We are looking at all these potentially very many parameterizing sets of relations. But we only need to look at the top part and at the bottom part. We only need to establish their complexity. If the top part is easy, everything below it is easy. If the bottom part is hard, we prove that everything in this interval is hard, according to the notion of complexity reduction that we have chosen. And this actually is a very powerful method to achieve results in complexity theory. Since I'm already over time, I think I will skip showing you the exact applications that have been proved with this method, but I hope I will be able to bridge you a gap, to build you a bridge between complexity theory and some nice algebra which can be used to establish results in computation. Thank you very much for your attention.
My question is, how can we base the relational cloud help to simplify computation and improve the interpretation of topological data in the high-dimensional data sets?
To improve what?
Improve the high dimension in topological data sets.
Data science.
Yes, I'm missing the first part of the sentence.
Sorry. How can we base
Yes, yes.
in relational clouds help simplify computation and improve the interpretation of topological data?
The interpretation of topological data. I have to say that I'm not specialist in data science and data analysis. So, first of all, I'm not sure if all this framework applies to the kind of problem that you're looking at, because probably the kind of data sets that you're looking at will use real numbers, I suppose, maybe.
Because it's very difficult to calculation. No sé cómo.
Que lo diga en español.
Sí. Bueno, no sé si podrás entender en español.
If you speak slowly.
Okay. Lo que pasa es que el recurso computacional para hacer análisis topológico de datos es mucho. Entonces, ¿cómo esto nos podría ayudar al momento de que nosotros lo quisiéramos implementar para hacer análisis topológicos?
But I still think the data that you have lives on real numbers. Well, then the answer is probably not at all, because this only applies to computational problems that live on finite sets. These are discrete computation problems, like problems with binary values, or tolerant problems, or such kind of things. Typical applications for these are like scheduling problems with finite possibilities or something like this. I think this doesn't help you at all, because your base set is real numbers, and this is far beyond what can be achieved.
Okay. Thank you.
Questions for comments?
Let me see one actual application, right? Maybe this goes into the direction of okay, this is some work that I have done with co-authors. We have looked at optimization problems connected to these constraint problems. So, for example, we have our constraint, and we have an additional information, a tuple which is as long as the solution. And then we're studying the following different problems. Find me a solution which is as close as possible to a given valuation of the variable. The evaluation doesn't necessarily have to be a solution. or the assumption is that the evaluation is actually the solution. Find me another solution which is as close as possible in terms of Hamming distance. So it means in terms of how many bits you need to flip to get from one to the other. Or find me the closest distance of any two distinct solutions. This kind of problem here is a generalization of finding the minimum distance of a code encoding theory, of a linear code. But we're generalizing it to solution sets of any kinds of constraint problems. And then with the help of the theory, we're able to obtain the following classification of all these kinds of problems. Each of the different colorful dots represents a different kind of difficulty. The green ones are all easy, the hard ones are all very hard, and I don't remember what the red ones are. They are also hard, but something in between orange ones. In particular, this method has been also used to prove finer complexity classifications of NP-hard problems. You may have heard about the distinction or the question between NP-hard and polynomial time solvable problems. If you can show that NP-hard problems are distinct from polynomial time solvable problems, you can earn $1 million, United States dollars. That's still open, one of the most important problems in theoretical computer science. People have been looking at to try to, because many problems have been shown to be all NP-hard, so all of the same hardness, but intuitively, heuristically, there are differences between these problems. Some of them are felt to be more hard than others, even though the reductions that we use show that they're in the same class. And there are other assumptions in complexity theory, like the so-called exponential time hypothesis, which says that the three satisfiability problem has no sub-exponential solution algorithm. And this is a very strong form of hardness. And the theory that I have been showing you has been used to show that many other problems are also exhibiting this very strong form of hardness. So if the three satisfiability problem has no sub-exponential solution algorithm, then many other problems also don't have a sub-exponential solution algorithm. So it helps us to distinguish more in some class of problems between problems which are very hard, extremely hard, and maybe some others which are not.
Thank you so much.
Thank you very much. It's really interesting here.
And finally, we have a relation, like a photo of the all together. So, how we se pueden mover para acá.
Se le va a coger.